Yeah, if it runs low on charge, tell me and plug it in. The wire is not low.
Yeah. So,
yeah. Let's see how long it lasts.
how do I switch slides here? Sorry.
Look at that screen. There's your mouse and use the arrow keys. I think it should be enough. Okay.
Okay, fine. Yeah. Okay.
Yeah. Try not to touch the mouse.
Okay.
But it might be.
Oh, don't touch this. Fine.
You can. I'm just saying that it might come.
Yeah.
Mouse might go to your side.
So, yeah. Hi everyone. I'm Sowrabh Sudevan I'm a finally a PhD student at IISER Kolkata, and this is like one part of my work on constructing error correcting code spaces from m-uniform states. Now, I'll try to explain each of these terms, like because there are when I started my PhD, I didn't know what were error correcting codes. I didn't know what were m-uniform states. So I'll define all of these things as I go along. So, so this part, yeah, we'll get back to this later. So I will first start with a minimum recap of quantum mechanics. So because I'm assuming there's going to be some students in the audience, maybe I don't know who might not be familiar. So, so in quantum mechanics, you have this is the notation we use for two distinguishable states, 0 and 1. These are vectors in some two-dimensional space. And the most general piece of a single qubit, a single quantum bit of information is given as some linear combination of these two things. So where these coefficients can be complex numbers. And this distinguishability thing will keep coming back to this idea about distinguishable states. So, and in quantum mechanics, the one non-trivial thing compared to classical information is that measurement is a non-trivial thing, right? You have information. Let's say you have some psi, which is some information, and if you measure, let's say measurements correspond to some operator, and measurements will collapse that state into the eigenvectors of that operator with certain probabilities. So you can get different probability distributions from the same state based on which operator you choose to measure, right? So this is a distinct feature of quantum mechanics, that measurements can disturb information, and the same state encodes multiple probability distributions based on choice of measurement operator or basis. And now, two quantum states are distinct or distinguishable if they are orthogonal. So the thing is, if you have state like 0, and 0 plus 1 linear combination equal this one, these cannot be distinguished in any one experiment. I mean, if you have one object which has this information and another object which has this information, they're in two boxes. In one experiment, you wouldn't be able to figure out which is which. You would need many copies to be able to figure this out. So now I have talked about everything we need about single particle quantum mechanics. When you have many qubits, so for many qubits, the state of a many qubit system is given by a tensor product, which is you do this kind of product and you vectorize it. This is what a tensor product is. And this longer vector represents the state of two systems, A and B, put together. And in general, an n-qubit system is described by a 2 to the power n length vector. It increases exponentially. So this is one interesting thing. I mean, it's not just a feature of quantum mechanics. It's a feature of, I guess, many variable probability distributions, right? You would have so many joint probabilities to keep track of. So and now, what is entanglement, right? With this introduction, entanglement it's a very simple linear algebra property, at least for pure states. I mean, not for, yeah. The thing is, if you have, let's say, this vector, 0, 1, like the state of two qubits like this, is not entangled because it can be written as a tensor product of two things. Similarly, some seemingly large superposition like this is still a tensor product of just two things. So this is also not entangled. This long vector, on the other hand, by just flipping one of the signs here, by making this plus to minus, now there is no way to write two vectors whose tensor product gives you this vector. So entanglement just means that there is this vector cannot be decomposed as two vectors. Or physically, it means that, see, the state of a quantum system is given by some vector, right? So that is the complete description of that state. So if the joint state of something, of two things, is a vector which cannot be written as the product of individual states of each of the things, then you can say that they are entangled. There is no separate description, separate complete description for each of those things. So now we just did a 1-0 type thing, as in what is entangled and what is separable. But maybe you want to quantify what is the degree of entanglement. So for that, we just have to quickly introduce one more thing. Like sometimes the state of a system is not exactly known. It could be like if you have the full information in quantum mechanics, you would have a specific vector. But otherwise, you could have a probability distribution over many possible vectors. It could be this state with some probability or this state with this probability and so on. That is where you have this idea of a density matrix. It's a classical distribution over a set of pure states. So if a state is well known, we have a specific state. And otherwise, you have a mixture of this form, some joint probability distribution over states. Now, if you're given the state of a system for, let's say, for two parts like A and B, now the description of A is, there is a mathematical procedure for doing this. Like you can construct the description in terms of a density matrix for A, which is done by taking the density matrix for A, B, and then tracing out the parts for B. Like you allow the B part to take all possible values because you do not know what that is. And like that, you trace it out and you get the description for A. Now, like I said, like if you know the full information about something, you have a specific vector psi. But otherwise, you would have some distribution over A, over the different states. So if the state is, if psi AB is entangled, then the reduced description of one of the objects will be some probability distribution over the different possibilities. And the entropy of this probability distribution, how spread out this probability distribution is what we define as the degree of entanglement. So now the entropy is the highest if all possibilities, all other possibilities are equally likely, which corresponds to this reduced density matrix being proportional to the identity matrix. So this would happen for all of these vectors. For all of these vectors, you have this 0, 0 plus or minus 1, 1, 0, 1 plus 4, and that other vector. All of these, if you take the description of any one of the systems, you would get something proportional to identity, which means that this state is, these states are all maximally entangled. And entanglement is useful for many things like key distribution, secret sharing, teleportation, all these things, but we won't be looking at that now. Our goal will be to look at what about if there are more than two parts, right? Like, so if there are more than two parts, then you need a way to, like, I mean, I gave a certain way of how to motivate this idea of entanglement for two parts. For more than two parts, there are multiple different ways of defining entanglement. And sometimes there are states which are highly entangled according to some measure, and then it's not that entangled according to some other measure. But these things may capture different uses that state could have, these different measures. So this is why, like, I found this in someone else's thesis, like all separable states are alike. Each multipartite entangled state is entangled in its own special way. And it's like something from some book, like about how all happy families are alike and each unhappy family is unhappy in its own way. So, so there are lots of unique ways, but like, I mean, I find this way to be very interesting. I mean, at the start of my PhD, I got interested in this. So these are called m-uniform states. So we talked about maximally entangled state as something where you take any reduced density matrix, it is proportional to identity. So why not look at, okay, you have more qubits, let's say 3 qubits. Any reduced density matrix of 1 qubit will be proportional to identity. That is, there can be, let's say, there are 5 total qubits, and any reduced density matrix of 2 qubits of 1 qubit, like there are 5 choose 2 ways of choosing 2 qubits. There are 5 choose 1 way of choosing 1 qubit. All of them should be proportional to identity. No? So this feels like a very natural extension. And so these are m-uniform states are n-qubit pure states with the property that every n-qubit reduced density matrix is maximally mixed. So this notion was first introduced by these people, and they studied this a bit, and they showed that for symmetric states, um, symmetric states are states where if you interchange the qubits, the state will be the same. And you cannot have more than m is equal to 1, as in you cannot have more than one uniform state. So, and some other interesting things. So now the basic idea is that these states have maximum bipartite, like I said, you have a clear definition of bipartite entanglement. So for multipartite, you just think of it as many bipartitions, and you maximize the entanglement for every such bipartition. So an m-uniform state has maximum entanglement across every m versus n minus m bipartition of an n-qubit system. So now one thing that follows is that if a state is m-uniform, then it's not just every n-qubit reduced density matrix that is maximally mixed. Every smaller density matrix is also maximally mixed, like m minus 1 density matrix. So if something is m-uniform, it is also m minus 1 uniform, and so on. This happens. And now this is a kind of popular topic. There's a lot of people who work on this stuff called absolutely maximally entangled states. So this is these are n-qubit states that are n by 2 like floor function uniform. So this is the maximum possible because both the sides should have the same entropy. This is something that you can prove from just simple algebra, that you have a two-party system. You look at the entropy of part A, that will be equal to the entropy of part B. So from that, you can show that the maximum amount of entanglement will be n by 2 bits of entanglement. So, and states which saturate this, which reach this highest amount, these are called absolutely maximally entangled states. And this paper showed that such states do not exist in qubits for n is equal to 4 and for n is n greater than or equal to 7.
Would you please repeat the definition? Like, yeah, I say that for any n-qubit states, you cannot, n cannot exceed n by 2.
Yeah. M cannot exceed n by 2, and where you have m is equal to n by 2, that those are AME states, where that is possible. So this first part of the result, like n is equal to 4 and n greater than 7, was shown by these people. And it took almost 10 years just to show the case that n is equal to 7 is also not possible. And these people, this Huber, there's a whole table of AME states. Like, so now the thing is, so in this table, okay, it's not very clear here. So this acts as the local dimension, as in this is qubits, this could be qubits, 4-level systems and so on, and how many number of parties. And we see that, okay, so 2, 2, this is like the Bell state. So we know that, so the green means that such states exist, and dark blue means they don't exist. And yeah, and then all these blues are not existing. It's just about here, it doesn't, these different shades just represent excluded by which bounds. So, and also in this thing, I mean, if you go to the website, you can see that by clicking on each of these cells, it will also show you the construction as an examples of these states. And then, which is an example for 3, 5, and so on. People try to fill in these blocks and try to find different constructions. So the white ones are things for which it is not known whether they exist or not, or what is a known construction. So, so like this, there's a lot of things. In the table goes on like so. Now these things, AME states, you see it in a bunch of different contexts. I've seen papers on. So one curious thing is this. See, this seems like a lot of constraints, right? You're taking an n-qubit state, you're taking all reduced density matrices like this, and they all have to be maximally mixed. That is a very strong set of constraints, and such states do not exist for many different cases. No.
But because we just see n-qubit any.
No. Oh, so here I talked about qubits. They could be higher level systems.
Yes. So the first column is the qubit, and the rest is.
You see, the qubit column quickly like ended at 7. There's no more. But you go to higher dimensions, they become much more possible. There's a lot more freedom in doing these things. So, so this seems like a very strong set of constraints. But there's also this fact that the most this was done by. Okay, they're not here. Not Dawn page, yeah. The most generic state, like over something like a very uniform measure called a Haar measure, over like let's say the set of all n-qubit states, right? It's very close to being AME, as in the reduced density matrix is near maximally mixed. So in the space of all states in a over a uniform measure, you see that these are quite common. But yeah, they are very close to AME. Now the thing is like having that exactly equal to identity. I mean, is there any extra use to that? That's a different question. But as a math problem, it's kind of interesting that there's a strong set of constraints, and can you actually satisfy this, and what are different constructions? So
You have to zoom out.
oh,
Maybe do
okay. So now back to m-uniform states. So examples of one uniform states, you have already seen the Bell state and this particular state, and even this like a GHZ state. You could have any number of qubits. All these are one uniform states. Now, so any reduced density matrix of one qubit is maximally mixed. Now, example of two uniform state, I'm the smallest example of a two uniform state is with 5 qubits. So it becomes quite large, like as in there are 32 basis vectors here. So now, yeah, there's a bunch of, it's not easy to see just from this why this is a two uniform state. Or so the length of the state, I think, like motivates the next part that I will have to bring in stabilizer structure. So you will see why stabilizer structure is useful to represent such states. So now the idea of stabilize before that, I have to talk about what is the Pauli group. So we have these 4 Pauli matrices. These are this identity matrix, and there's this X matrix, Y matrix, and Z matrix. These span the space of 2 cross 2 Hermitian matrices. So they are kind of useful for a lot of things. And now all possible tensor products, like I've already shown what a tensor product is. I mean, I've just shown it for vectors, I haven't shown it for matrices, but you can, you can look it up. I mean, so consider all possible tensor products of n Pauli matrices. These plus some plus or minus I and plus or minus 1, they form the Pauli group. So Pauli group, as in they're closed under multiplication and associative law, and they inverse exists and all these things, the usual group stuff. So now psi is an n-qubit stabilizer state if there exists n independent and commuting elements of the Pauli group, such that these of the Pauli group Si, such that Si psi equal to psi. That is, psi is the +1 eigenvector of all of these n independent and commuting elements. So this is what a stabilizer state is. Now, to give an example, like even this particular state that we had, this Bell state, 0, 0 plus 1, 1, you can think of it as the state which is stabilized by these 2 operators, as in x1, x2, and comma z1, z2. Action of these 2 operators will give you the same state. And similarly, this GHZ state can also be given by these 4 operators. So there are 4 qubits here, so you need 4 operators. And that very long state that we wrote, that again just takes 5 operators. So the thing here is that the advantage, like you will see it as to take larger and larger qubit states. So specifying a generic n-qubit state requires 2 to the power n complex numbers. It grows a lot. But if that state was a stabilizer state, it's not true for any state. It's only if it's a stabilizer state, then you can actually represent it in 2 n square bits. So the n square bits is coming from, if there's an n qubit state, you will have n Pauli matrices. Each of those Pauli matrices can be thought of as a 2-bit thing, right? Because there are 4 Pauli matrices, so 2-bit information. And you have n length string, and there are n such strings. So that's why there is 2 n square bits. So 2 n square is much better than 2 to the power n for large enough n. So
how is coming?
The 2 is coming.
2 plus 2.
No, there are 4 poly matrices, right? So you can choose, you can identify 4 things with 2 bits of information. So this is also like the essential argument of that.
There's a question. This is stabilizer proof that unique for every state. Right?
Okay. For a stabilizer state, it has one stabilizer group associated with it.
Okay, but for stabilizer proof, there could be multiple stabilizers.
No. Okay, if you have it depends on the. Okay, so if you're in an n-qubit space, right, and your stabilizer group, the cardinality of that, like the size of that is 2 to the power n, then there is one unique. There can be, I think I'll get to the idea of stabilizer codes. So that is like with a smaller group, you can have, it can stabilize a larger space. If you have the full group, like as in if you have n independent and commuting elements or n independent and commuting generators for that group, then you will be able to span exactly one state. If you reduce that, take a smaller set, like throw out some of the things, you'll be able to span a space. Right? So even the essential idea, there is some thing that in quantum mechanics and the initial motivation for, let's say, quantum computation, right, was of this form that that generic state information in quantum mechanics is given by some 2 to the power n length vector, right? So if you have to, like, let's say, try to simulate it on a classical computer, it becomes quite expensive. You have this 2 to the power n length vector, which has to be like time evolution in quantum mechanics is given by some matrix acting on that vector. So that matrix also has to be 2 to the power n cross 2 to the power n. So this is like in nice sense, you can see that this is computationally very expensive, because the size of the matrices are increasing exponentially with the number of qubits. So then there was a motivation, but so there is some idea called the Gottesman theorem that if you have a circuit, like a quantum circuit, where you only go from stabilizer state to stabilizer state at each point, then your state description is also efficient. It's at least not exponential. It is 2n square bits, and each of those matrices can also be made smaller. They can be 2n square plus 2n square. They can be efficient. So this is interesting because see, some of these examples that we wrote here, they are entangled states, right? They are entangled states, but they have efficient representation. So entanglement alone is not what is interesting about quantum mechanics. So, or at least what makes quantum computation interesting. Like it's a bit more complicated than that. But yeah, this is going to a different topic. So I just wanted to show you what is the point of this stabilizer structure. And so now we'll be looking at states which have this structure. And so to have this structure, I told these things, they have to be, these matrices have to be independent of each other, in the sense that product of 2 things shouldn't give the other. And they should also commute with each other, as in like AB should be equal to BA. Now, one simple way to get that is by following a particular recipe with graphs. So these are called graph states. You can see them as a subset of the stabilizer states. But the basic idea is that, see, if I draw any mathematical graph, like with, let's say, 4 vertices in this case, so this can uniquely represent a 4-qubit state. So the way you do it is, at each vertex, let's say this vertex, you have, at each vertex, there will be an X for that vertex, and there will be a Z for whichever vertex is connected to that. Like 1 is connected to 2, so there is a Z2. Similarly, 2 is connected to 1, 3, and 4, so there is Z1, Z3, Z4, and there is a 2 at that spot, and so on. So there will be X in the middle and Zs for all the connections. So like this, you will get 4 operators. And just because of following these rules, you automatically end up with a set of things which are, independent, that is obvious, because the X's are at different sites. But even they commute.
So what is this? You said you had 4 matrices. These are 2 plus 2. What is this? The subscript of these matrices?
So this means that, okay, this means that there is this X1, Z2 means X, tensor product Z, tensor product identity, tensor product identity. Like wherever I have not mentioned, there are identity matrices there. So you fill this in to make a 4-qubit, like 2 to the power 4 cross 2 to the power 4 matrix by filling in identities in other place there.
In other words, there's not anything for the node. It actually XZ, ZX, ZZ. But he wants to put for ith node, he wants to put X in the ith place.
Oh, so that's exactly right. Yeah, so only the sequence.
Yeah, only the sequence. Yeah.
But again, it also considering there is a commuting.
So when you do the commutation for so this x1 z2 exactly means x tensor product z tensor product I tensor product I. And the second location has a z, the first location has an x, and like you said, same thing.
So these are the tensors.
Yeah, these are sequence of tensor products. Yeah. So like for example, if you multiply, let's say 1 and 3. To see that they commute, right? See, you can just multiply, let's say 1 and 3. You will see that, you only have to multiply Z2 and Z2 there. I mean, because the others are on different places, right? So Z2 square is identity. And I mean, so it's like they commute. And you can check, like everything commutes. This happens like if you take an undirected graph like this. You follow these rules on an undirected graph, you automatically get commuting operators. Because I guess on an undirected graph, something is connected to something, that something is again connected back to something. So what am I saying? Yeah, if 1 is connected to 2, 2 is also connected to 1. So you will have x, z, and you will also have a z, x. So there are 2 anti-commuting rings. So you always get pairs of anti-commuting rings. So the overall string commutes by following this. There are other ways of doing this. This is like this one very simple way of doing this. Just a method of getting commuting operators. So
We can treat the graph and not understand it completely. So we have to stabilize it.
Yeah.
We put them in a space. Then we're trying to connect them.
No, the graph is telling you what are the stabilizers. Like given any graph, that can be the picture for a state, for a stabilizer state. As in, instead of writing the state with a computational basis or whatever, like with a long vector, you can just draw a graph. That graph represents the state. And the way you actually understand what the state is, like the stabilizers of that state, you can know from the connections of the graph. As in, see this, if you draw a 4-qubit graph, you're talking about a 4-qubit state. And the first stabilizer is given by, look at the first vertex, it's connected to second vertex. So at the first vertex, you put an x1, at an nx, and the thing it is connected to, you put z. So that gives you the first stabilizer. Like here, 1 is connected to 2, so you have a Z there. Similarly, 2 is connected to 1, so you have a Z at 1. It's connected to 3, so you have a Z at 3. Connected to 4, you have a Z at 4. And like this, it's a way of writing down, like in general, you get the poly group. It's a lot of tensor products of these. Which of those things commute is not easy to see, right? I mean, so here, if you follow the graph rules, you will always get commuting operators.
Okay, so if I want to 4 stabilizers for like 4-qubit, I'll just draw a graph and then I'll come up with the thing.
Yeah, with the commuting operators. Yeah. So, and it turns out that like there is something called, so when it comes to entanglement, there's like entanglement is preserved under local unitary transformations, which means that you could have a unitary matrix happening on each of the qubits. That does not change the entanglement. And see, I told you that these set of states which have stabilizers given by graphs, they are a subset of the stabilizer states. These are called graph states, but they're not exactly a subset in the sense that in terms of entanglement, they fully span stabilizer states. As in, you could do local unitary transformations and you could span the whole set of stabilizer states, starting from just graph states. So if you're interested in properties of entanglement for stabilizer states, you could just look at the graphs. And in the graphs, things like entanglement sometimes is clear from the connections between things. Like the fact that there is an edge between 1 and 2 immediately tells you that there is entanglement. It doesn't tell you necessarily the degree of entanglement, but it tells you there is entanglement. These are not, 1 is not separable from 2. These two vectors are connected.
Would form the generator of the stabilizer?
Yes.
So, why do you call them graphs? Because they look like just trees.
Like no, just a mathematical graph, like just vertices edges. That's it.
Yeah, but you know more about it. They're special kinds of graphs.
Yeah. This is a special case, but it doesn't have to be this. It can be some other graph also.
But if you
I drew a tree. Yes.
equal the definition. For every vertex, you have one GVD.
Yes.
And then n-1 adjust to be enough to get your full information, right? You want to get all GVs for all V belong to the vertex.
Yes.
So you need a connector that thoroughly. But n-1 adjust should give you full information about the graph state.
No, get the graph, and that graph specifies different.
Yeah, but so I take the graph and it gives me the graph state. I remove some edges, you see uniquely the same graph state.
No, if you remove my graph.
It's not necessary, but what is the minimum number? You need a topic graph to represent it, not picking.
No. Each graph means one state. Like if you remove some edges, it's a different graph. In this problem, it's a different graph.
Yeah, but if I add one edge to this.
It's a different graph then. I mean, it's a different state.
It's like saying that.
But I mean, you already named your GP, so can change it.
No. If I add a new edge, then for example, if I add this edge, right? Then this operator will become x1, z2, z4. This will become z2, x4, z1. Like the operators change according to the graph. The operators are written according to how the graph is.
Yeah, that's the definition. G is X, XV, ZW for all just neighbors of B. Yeah.
So if you draw different graphs, you will get different operators, and that's a new state. Whether those states are distinguishable is a different thing. Like in the sense that whether they are orthogonal or something, that is tough to see. Like that we will get into maybe later.
Is there any constraint on the type of graph that we like? Does it have to be a tree or
No, it doesn't have to be a tree at all. I think maybe I chose a bad example. It can be many. We will see more graphs. See, it needs to be a graph without any self loops and undirected. So I guess that's a simple graph, right? Yeah. But there are different constructions. See, the thing is that these strings, these Pauli strings, need to all commute with each other. And this is one way of making them commute. But there are other constructions. We will see other constructions. So, I mean, so during my PhD, I was interested in trying to construct these m-uniform states. And working with these large expansions is hard, like seeing, taking all these things. So then there are these very efficient representations of states in terms of graphs. Like you just play with these graphs and you see which edges to cut and, try to make sure the entanglement is high.
Why having the edge means that is entanglement? Because it goes through these.
So
it's okay. I was just asking if you have like someone thinking about it. Otherwise, you can.
I mean, intuitively see if you have something. Okay, like let's say this kind of state, right? 0, 0 plus 1, 1. This thing is equivalent to just two vertices with an edge connecting them. It's like one set of like two vertices with an edge connecting them is like a bell pair. So you could have a bunch of such things. Like if somebody gives you a graph which is just dots and they are connected like this, you would see that if you cut this by parting, how many edges you're cutting,
Then what is this two dots?
Oh, I mean, here there's a 2 qubits, right? So there'll be 2 dots in the graph.
No, I'm saying without it. If you have a graph with just 2 dots.
No, that would just be a product state. It would exactly be the plus state. Yeah. So another thing is, okay, so maybe not from the stabilizers, it may be easier to motivate by from the circuit side. So this is one way to get the state. Given a graph, you get the state by writing the stabilizers and find the state for which these are the stabilizers of the state. Another thing you could do is you could have, let's say, 4 qubits prepared in the plus state, like 0 plus 1 equals superposition. And you, based on these edges, you apply control V gates. So they are like entanglement gates. So you would apply 1, 2 gate, you would apply 2, 4 gate, you would apply 2, 3 gate. So you see that there is an entanglement between 1 and 2. Yeah, it's more clear in that.
When we see this entanglement between 1 and 2, we just take the ideal state corresponding.
Yes.
So in that 2-node case where they're not connected, the stabilizer group is identity.
No. The stabilizer group there is x1, x2.
But they won't.
Because see, the state is plus plus,
Yeah.
So now the question, okay, so which graphs are m-uniform, right? I mean, so this is something I worked on. So like to get a one uniform state, all you need is like the minimum thing you need is you need every vertex to be connected to at least one other vertex. There should be no isolated thing. There should be a path between everything. Then it'll not a path. That's not important here. Yeah, it's just everything should be connected to at least one other things. You can have disconnected parts. That's not important. This will make it one uniform. So even the fully connected state, which is actually equivalent to this GFD state. So in a lot of different applications, GFD state is seen as this very highly entangled state. But for this purpose, it's not that highly entangled. It's just one uniform. However large you make the GFD state, the degree of uniformity is just one. So, and that very long superposition we wrote can be simply represented by this graph, right? It's just a cycle with 5 qubits. So there's a very simple way of looking at the graph.
Fully connected graph is the GSM.
Yeah, fully connected graph is local unitary equivalent to GFD. So, and yeah, that two uniform, like the smallest example you can write is something like this. You could just write a 5, like a cycle. And for 3 uniform, the smallest thing you can write is this kind of graph. You have like a prism with 2 triangles on both ends. So this thing you can show is.
How do you see this?
Oh, how do I see this is 2 uniform? You can prove it. I mean, yeah.
I mean, is there like a visual? Like just at point like this.
Yeah, so yeah, there is, okay, so you have seen, so you can actually, so there's a graph, like adjacency matrix for a graph, right? So it turns out that for graph states, if you write the adjacency matrix, and so you have this adjacency matrix, and you want to look at, let's say, the entanglement of this set of vertices against this set of vertices. You could actually look at the rank of this off-diagonal block. I mean, it just comes from the algebra that the rank of this block. So in graph states or even stabilized states, entanglement always comes in discrete chunks. Like it's always 1 bit, 2 bit, 3 bit of entanglement. They don't come in between values. And it corresponds to the rank of this off-diagonal block. So with these graphs, you can play with that. You don't need to think about all the other things. You can just try to make rearrangements of the matrix and make sure that all the off-diagonal blocks are very high rank.
So for a completely connected graph, those are not high.
Yeah, the rank is actually very low. Rank is just 1. Like a lot of things just, I mean, they stack on top of each other. So fully connected graph, you can see, all this off-diagonal thing will be all ones. So rank will be very low. So now, then we put a more general result, like a class of states for all integer values of m, like 1, 2, 3, 4, whatever, uniform. But I will get to that a bit later. Now, we've talked about what is m-uniform. We've introduced what is graphs and stabilizers. So I'll quickly go into just error correction. So what we're looking at is, so this is just classical error correction, no more quantum things. So you want to send, let's say, some information from some person to whatever, like across some channel, and information you're sending bit strings. So now the channel has some noise, which makes some of those bits flip. I mean, we don't know all the other details. We just say that there is some probability that some bits are flipping due to the noise. So the simplest code one could think of is something called like a repetition code. As in, like, if I'm not clear, I repeat something a couple of times, it's more likely to be clear. So you, instead of sending, whenever you want to send a 0, you send 3 zeros. Whenever you want to send a 1, you send 3 ones. Now, 2 mistakes have to happen, and the person receiving it will look at a majority vote. Like every block of 3 things, they will look at which is higher. And then automatically now the probability of wrong information to be received has gone from p to p square. So 2 mistakes have to happen. 2 independent mistakes have to happen. So if the probability was like very small, like whatever 1%, this becomes even lesser. It becomes 0.01%. So error correction is all about storing information in a larger space, like you are using redundancy to give some robustness, like to the information. So Now, wait. And like a more non-trivial code is something like this 743 code. So it's like you can, okay, so you have 4 independent things, like 2 bits of. Fine, there are 4 independent possibilities. There are 2 bits of information. And like basically you can have, you want to send either 0001. So over there, to send 1 bit, you have to store it in 3 bits. But it can be more efficient. You can store in 7 bits. It's more packed here. And this can correct the same amount of distance. So the idea is that, see, you will map 00 to this vector, as in whenever you want to send a 00, you would send this vector. Whenever you want to send a 01, you would send this. 10, you would send this. And 11, you would send this. And now what you would do is the receiver would actually add up like let's say wherever there's a 1 here, like for whatever you're receiving, right? So wherever there's a 1, you will add the value of that bit to the value, let's say, of the 2nd bit, to the value of the 4th bit, like mod 2, to the value of the 6th, or this is the 5th bit, and so on. So this would give you a 3-bit string. This 3-bit string will be able to uniquely identify. So 3 bits means 8 possible outcomes, right? So here there are 7 bits. So you can identify an error on each one of these 7 bits, or one possibility is no error. So that's how the 8 packs this. So this is it's called a perfect code because everything is packed like this very nicely. And so this is another. So a lot of classical error correction involves working with these or more complex structures. But the basic idea is that you are able to store. You store something in a larger space and then do certain kinds of measurements to uniquely identify which qubit had an error, and then you correct that, not qubit, which bit was flipped, and then you flip it back. No, the receiver can do that. So now,
With this error syndrome, right?
yeah, there are yeah. So this is how it's in classical error correction, that you will be able to identify where the error took place and then you reverse it, and that the discreteness of information is necessary for this. You cannot have this with continuous variables. You do need discrete information to be stored discretely for this to be possible. Now, initially, I mean, this was a thing, right? In the early days of quantum, like, is quantum error correction possible? Because in quantum things, the information is some alpha times 0 plus some beta times 1. It's like a continuous variable. So errors can also be continuous. Some arbitrary unitary can happen and things will move around. So it turns out that quantum error correction is possible. So this was shown by Shor, like by explicitly constructing a code. So now, like one thing is, like, let's take a code that corrects one error. So you could map one X error. So you could map 0 to 000 and 1 to 111. This is exactly like the repetition code. And you would be able to identify where the X error happened by, I mean, if you assume that the only thing that happens is X error on any of these qubits or not happening, right? If that is the only thing that is possible, like, then you can find the X error location by measuring this Z1, Z2 and Z2, Z3 measurement. This will uniquely tell you where the X error happened. Now you can simply flip this to a code that corrects one Z error by taking 0 to map to plus 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 and 1 to map to minus minus minus. And now the Z error location is identified by measuring X1, X2 and X2, X3. So, and there is a procedure for combining these 2 codes. So the thing was that initially people thought that quantum errors are like some unitary happens. It's a continuous thing. There is no discreteness here. But what Shor did was that he showed, okay, so you can pick up these 2 types of errors, these 2 orthogonal types of errors as X errors and Z errors. You have a code for correcting X errors. You have a code for correcting Z errors. And then you combine them. Like basically you encode everything into 3 bits, and each of those bits you encode again using the other code. So that's why you'll store one thing in 9 qubits. And by doing this, you will get this kind of object. And the stabilizers are longer and not going into those details. But it turns out that by doing this, you can actually correct any single qubit error. Like even if some arbitrary unitary happens on this, you can correct it. So why this happens is that, like, while the errors themselves may be continuous, you are doing measurements, right? And quantum measurements are not like classical measurements. When classically, you know what are the values of a register. It's a non-trivial process. Here, the act of measuring changes the state. And doing these stabilizer measurements, actually, like, I mean, not necessarily stabilizer measurements, but still, doing measurements can discretize the errors. And by choosing the proper basis, you can turn all errors into either X, Z, or product of X and Z. Like both errors happening. So instead of in classical bit computing, you have a bit flip. Here you have different types. You can either have a bit flip or no error. Here you have a bit flip, something called a phase flip, or a combination of both, or no error. So you have 4 possibilities instead of 2 possibilities. But then a lot of the math from classical error correction actually carries over. You can all the results from GF2 go to GF4. I mean, I won't go into these details, but a lot of things do carry over quite smoothly. That it's not measurements do make things discrete. So now again, stabilizers. So we saw that those. This Shore code. I mean, historically it came a bit before the paper on stabilizers by Gottesman and these things. So then, like this Gottesman in 1997 formalized this whole thing and came up with the general structure of linear quantum error correcting codes. So yeah, I think one of you had asked this question. So if you you talk about, like, in classical codes, you have these Hamming spaces. Here you have some slice of the Hilbert space, and that is specified by, like, if it's an n-qubit Hilbert space, if you specify k less than n stabilizers, you will specify a logical space for n minus k qubits. You can specify subspaces by specifying less stabilizers. So a simple example is, like, let's say this thing 0, 0, 0 plus 1, 1, 1. It's a stabilizer state with these 3 stabilizers, Z1, Z2, Z2, Z3, and X1, X2, X3. And now the span of, like, instead of this specific vector, the span of these 2 vectors, any linear combination of these 2 vectors. To get that, you simply have to just remove X1, X2, X3. The span of these 2 things will give you, like, a smaller vector will give you that space. So, fine. Now, yeah, I think we have most of the pieces. So now, where is error correction and m-uniformity? Like, what is the connection between these 2 things? Okay.
First point, it's like in stabilizer state, we have a n stabilizer. I mean, we choose n such that it is equal to Pn by n.
So it belongs to Pn, yeah.
Yeah. Suppose we have a 5 qubit thing, then it's just 5 stabilizers. In
Yeah.
that case, we have 1 stabilizer state, but over there it's like n minus n qubits to power 0.
Yeah, 2 power 0 is 1, right?
Yeah.
So it's working out well, no? So, yeah, it can be shown that, so for an m-uniform state, the expectation value, so of some operator with support on, say, OR is a tensor product string of Pauli meters, like just a tensor product of Pauli operators, which acts non-trivially on R qubits. So there are X, Y, Z, all these things on R qubits. Other places are all Z. So for an m-uniform state, this expectation value can be shown to be 0. We have a proof, and there's also the proof by Arnaud and Cerf. I mean, but it's quite simple to do. Now, this thing, from this, you can actually get, like, so there's some operator with support on R things. You can break it into 2 operators with support on, like, R things where R, okay, I think I should have written this. R belongs to 1 to M, right? It is at most M. So consider the case where it is OM. Now that can be broken down in 2 operators, like O1 M by 2 and O2 M by 2.
Or R is real.
Yes, R is like an integer. Yeah. No. Yeah, R is just it's an integer. I think this N is wrong here. Yeah. So this is like the weight of the operator. How many? Yeah, it has to be. Yeah. So Yeah, so you can break it into these two operators. Now, from just this picture, you can see that some Pauli string acting on n by 2 qubits times psi is orthogonal to some arbitrary Pauli string acting on psi, right? So the state is taken to orthogonal vectors under the action of Pauli strings of length up to n by 2. So we are getting, so I told you we'll get back to this idea of distinguishability. When are quantum things distinguishable? When they are orthogonal to each other. Like that, if two vectors are orthogonal, okay, if two vectors are not orthogonal, it means that there is no one measurement to identify between them. But also, if two things are orthogonal, which I haven't said earlier, that if two things are orthogonal, there will exist a procedure to uniquely identify them in one measurement. Like there is some operator you could measure and you could know that this is this and this is this if they are orthogonal. So here the m-uniform condition implies orthogonality under some set of Pauli errors up to some distance. So in fact, therefore, an m-uniform state is an error correcting code with unique syndromes for each Pauli error on up to m by 2 qubits. And by the linearity of quantum mechanics, this ensures arbitrary errors on m by 2 qubits are correctable. Like if you can correct all Pauli strings up to some distance, you can also correct all linear combinations of those Pauli strings up to that distance. So this thing was done by the Scott and then Huber and Grassel, who looked at these kind of codes. So there is, thanks. So there is this. So there is these codes all have unique syndromes. So one thing is in classical error correction, you have unique syndromes, as in the sense that which is not even mentioned because it's taken for granted. You correct an error by knowing which bit was flipped, and then you flip that bit back. In quantum error correction, it is actually possible to not know which error took place, and you can still, get back the relevant information. Like a simplest example of this is something called the toric code. I don't know if I should go into this at all. Yeah. So this is another way of writing down. So here, let's say you draw some kind of torus like this, and then you have here these dots, that the edges, they represent the qubits. Like you can draw this picture, these edges represent the qubits, and you can write stabilizers where each of these boxes is one stabilizer. Like as in each of these boxes is x, 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 and each of these things, like the cross things, they are stabilizers with z's. So this way also, by writing a set of stabilizers like this, they will end up always commuting. And there's one more thing that you actually do not have. You will see that if this thing has periodic boundary condition, that it's on a torus. You will see that you will have two less stabilizer generators. So I think two less independent stabilizer generators. And because of this encodes a space. It's not one state. It is a space, a 2-qubit logical space, which you can define with this picture. And here also you can measure these, some information encoded in the space. You can measure these things and you can correct the errors, but the errors are, you won't be able to know which errors happened necessarily. So these are degenerate codes. So now the thing that, okay, so we have n-uniform states are non-degenerate codes on the other hand. Like they are, you can know which error happened. And so what, okay, I think I don't have a slide for that. So what what we had worked on is we had shown that for a certain class of physical systems, their ground states, now I'm using a lot of words randomly, but yeah. For a certain class of physical systems, the ground states of those things are these kind of m-uniform states. And now the ground states do not actually have any space to store information. They have enough stabilizers to uniquely specify the state. So you have no thing. So what can you do with one code word of an error correcting code? Like if you just have, why did it jump? So it turns out that even if you have one code word of an error correcting code, you can actually do something with it. So what you can do is see, since these are codes which can uniquely identify which error happened, you can use them in experiments to benchmark the error rates in quantum computers. As in, you can what that means is, see, on a quantum computer, there are various like X, Y, Z errors that happen with certain probabilities on each of the physical qubits. You can, this is not the only way to do it, but this is one way you could do it. That you could prepare that state on the quantum computer. Like here, you perform some circuit, and before these dotted lines, you have prepared that state. And then some error happens, let's say, on this qubit. By doing some series of steps here, you can actually figure out whether X, Y, or Z happened here. And you could do this many times and you would get various probabilities of X, Y, and Z. No? And now there would be problems coming from, okay, wait, I'll get to that later. So these are some plots from some, these are simulations, that's not important. These are the demonstrations. So these are run on this IBM machine. And so these green line represents the Z errors. X and Y lines represent X and Y errors. And this X-axis is the time, and is the probability of that error. So as time passes, the errors increase. The probabilities keep increasing. And you will see the slope for Z error is higher than the slope for X and Y. Now Z is starting at a higher point. Now that is because in our state, the preparation state itself, we are using a lot of control Z gates and so on. So this introduces a lot of bias. There are extra errors coming from that. So that we can show that it's coming from that by, instead of producing like that state, it's preparing the ZXZ state. We could instead prepare the XZX state. This is just local unity difference, but it has the same m-uniformity or whatever. And by doing this, we now see that X now starts at a higher chance than Z. So it's just coming from the initial preparation thing. So the important thing to keep track of is the slope. The slope is independent of that. So you see that here also the Z slope is higher. So you.
And what is the
So those are the, so this particular state that I prepared, those are the, like at this point, those are the stabilizers of that state. They have the form of Z1, X2, Z3, and so on, like go cyclic like that. So, but preparing that introduces some bias, which is why that initial error is so high for Z. You see that by preparing a different state, that bias can be changed. Now X is high. So the slope, like here, the goal is to find out what is that environment for that quantum computer, right? You want to know what are the error rates on that thing. And not, so that we are able to find out by, you can get to the biases by using different local unitary versions of this state. So now this is one thing you can do with one code word. Another thing is, so building logical spaces. So here the idea is like, let's say you have this state. This is some state 1 to n. And now, okay, let's forget this m-uniform thing. This is just some n-qubit state. And I have some qubit which has this arbitrary information, alpha times 0 plus beta times 1. I can apply some gates, control Z gates, or some entangling operations between this ancilla and some set of qubits here. And then I can measure this in the X basis. And by measuring this, I can actually produce this kind of linear combination, alpha times psi plus beta times Z acting on those set of qubits, psi. So this is a way to, like, you're sending this information from here to here. It's actually teleportation. I mean, because there will be some plus or minus here based on the probabilities. And so that classical information you have to send to these people to be able to correct whether it is plus or minus. So you can actually, so now the thing is, if psi was an m-uniform state, this object you have produced is like an m-uniform code, right? I mean, when does it become an m-uniform code? So that is the question. And we showed that if the set of things that you entangle with is greater than m into m plus 1, this object will be m-uniform. So it doesn't matter which things you connect to, as long as you connect to at least this many things. This is like a sufficient condition that you can, so this is a way to produce, so like even the earliest that short code, right, is kind of an example of using two classical codes. They have used two repetition codes to produce a quantum error correcting code. Here, what you're doing is you're taking an entangled state and, okay, maybe I should get to that point a bit later. Yeah. So this is one condition. And this measurement-based method here applies to any state. We teleport information from ancilla to the registers hosting another state. Now, like So what we are doing here in like the full notation or whatever. So an m-uniform state is an n0 m+1 code. No? I write 0 because it stores 0 logical information. There is only one unique state. Now with this method, we have built an n1 m+1 code. Like you have stored some arbitrary information, and if a is greater than m into m+1, then yeah, this is still m-uniform, so it has that error correcting property. So you have made the 0 into a 1, and the stabilizers modify when you do this procedure. Like the initial state has a set of stabilizers Si, the stabilizers of the encoded thing will, the Si's for all i's not belonging to that set A will remain the same. But for the ones that belong to that set, you will take products of stabilizers. You just use a bunch of stabilizers and get a, that's how the degeneracy comes. So then some work that we did after that was mostly trying to expand on this. And then how much information can you store? Like we made it n1. How large can you make that one? So this is where that thing comes in. So you can actually have a lot of ancillas, and they could be entangled with many different sets, like sets of qubits A1, A2, AK. So these sets of qubits can be seen as the same way as like these kind of codes, right? You have these 100, whatever, these kind of things. So you could have, let's say, if there was 7-qubit thing, there would be a 1 wherever it is entangled to that ancilla, and there would be a 0 where it is not entangled to the ancilla. So this kind of picture can be seen as a way to combine a classical error correcting code with an entangled state to give you an error correcting code. So now the question is, which classical error correcting code is interesting for this? So one simple thing is that any classical binary code with distance greater than m into m+1, which just follows from the previous thing, is good for this. But maybe you don't want this much distance. Like this much distance will require a lot of connections. You need m² connections. You may need a smaller number of connections. Okay. So you can actually do it with much less things. So here are the procedures. You start with an m-uniform graph state. You choose some classical code with some distance. You entangle the qubits according to the code, the matrix, generator matrix. And then you measure all the things and then apply local unitary connections. And that's how you prepare the state. So even that Shor code is like a way of combining two classical codes to give you a quantum code, like two classical codes in different bases. That is an example of a more general idea of CSS constructions. So here the thing is, you have you look at, so here we are looking, I guess our motivation came from the entanglement side. So we are starting resource is an entangled state and how to turn that entangled state into a code. And the input is which classical code is good for this. So the condition that this is, it's not necessary. The actual necessary and sufficient condition is this particular thing, which is like ZCE is like, okay, maybe I'll skip that. There is an actual necessary and sufficient, like there's a group theory condition. And then we took that condition and we looked at which code satisfy this. And then there are specific things which give back some of the well-known codes, like 513 and 823 codes. These are like very packed codes, packed as in this, there's an optimum amount of redundancy for the error distance that is there. And we have a general class of codes that hit that optimum amount, like a general class of codes which we call tent peg codes because of this picture. It looks like a bunch of tents, and these are like the pegs of a tent. So, and now one thing is with this whole procedure, a nice thing is that logical qubits can be encoded and decoded independently of one another. Like you could send some information in, and I want to decode, let's say I want the 5th bit for some purpose. I don't have to decode the entire block. I can just take out that thing. I can individually decode and encode things as I prefer. So yeah, so this work was done with these people. Like the first work was like about showing that a class of physical systems have these kind of error correcting codes as their ground states. That was done with these people like Daniel and Iransala and Emmanuel is my advisor, Sorindas. And then the last part of this had that idea of how to encode some information?
The screen share somehow stopped. Maybe you press something. Oh my god! I hope
So, and the last, then we expanded on that idea of how to build these code spaces. Like it went a lot more into the error correction side of things. And so with these people, Ashwant and Nupur and Naveen Kashyap at ISC. Thank you. These are just the
Any more questions? There are lots of questions. We have like.
But that was good. I had less slides. I was worried that I'll finish in half an hour and I'll be standing here.
No. People are very, it's very interactive.
Oh, that's nice. Yeah.
If not, then let's say speak again. Yeah, new code is also stabilized code.
Yeah, it's also stabilized code. Yeah.